Hello everybody, welcome back to another Engineering Statics lecture video. Now, before we begin, I just want to say that I hope you guys are doing well, surviving your second week, and having fun so far. Engineering, it's a very passionate thing. It should be a lot of fun. If you guys aren't smiling, you're doing it wrong, but, well, let's be honest, you guys are first years, chances are you're not smiling. And unfortunately, the smiles will probably go away if you still are smiling, because in this topic, we're introduced to the first kind of road bump I would say students have when it comes to this course. This is the first topic that I find a lot of students have a lot of trouble grasping, and then they really mess up on this topic in the midterm. So I'm going to try my best to explain it nice and clearly, and hopefully you guys understand it and you guys will be good to go for the midterm. Now, like I said, I'm not teaching this semester, which is great. Or I guess not teaching this particular course this semester. So I'm able to give some final and midterm advice, which is great. If I was teaching it, then I have to kind of keep my lips sealed because I can get in trouble. Now, since I'm not teaching, I'm going to give you guys the first secret. Typically, at the University of Alberta anyway, the first midterm question is what we're doing here in this second week. It's going to be 3D Cartesian vectors. Now, the first part of the midterm is going to be focused on that resultant force, or the first part of the question, finding the resultant force. In the previous two videos, we said that's no problem. We can find those resultant forces. Now, the second half of that first question is going to be related to this, dot product and projections. So let's discuss what those are. So again, if we look back at the previous two videos, we talked about Cartesian vectors in 3D, and we said that there's going to be three possible scenarios that we have, which we have to calculate the components of these 3D vectors. The first case, which I call the trigonometry case, is when they give you a force vector in 3D and they give you two angles. The first one is what the angle the force vector makes with the xy plane, and then the second angle, theta 2 there, is going to be the angle inside of that xy plane. We said this one's a little bit tricky, but we have nice calculations. We can do it and find all the components in 4 calculations. It's not too bad. The second case is the easiest case, which is the coordinate direction angles case. In this case, they give you the 3 coordinate direction angles for your vector, alpha, beta, and gamma. And if this is the case, we have formulas for all the components. We just substitute everything in. We're good to go. Now, in the last video, we talked about the third case, which is position vectors. And in this particular case, they don't give us any angles, but rather 2 points along the line of action of the force vector. We said that this looks a little bit scary, but it's actually not too bad. So again, referring to the midterm, the first question, the first half, is usually resolving these forces into their components and then adding them together. It's going to be one of the 3 cases. You guys are saying, you know what, Clayton, easy peasy, I'm ready for the midterm, or at least the first question. And this is when I say, well, hold on. There's 2 other things that they're going to ask you in that first question. The first one is, what is the angle between 2 vectors? So we discussed a lot about the angle a vector makes with the axis. But what about the angle between 2 vectors? So that's going to be the first thing we touch upon. And then the second one is, what are the force components in an arbitrary direction? If I have a force vector in Cartesian vector notation, I know the x, y, and z components. But the professor might just be laughing at you and say, okay, I don't care about x, y, z. How about in this random direction? So that's where it starts to get a lot of students, is once we introduce random directions. And that's going to be the second half of this video. So the key to all of these is actually going to be something called dot product. And this is going to be kind of the major exam question, this dot product. So in 2D, it's very easy to determine angles vectors make because it's 2D. It's very easy to visualize, draw it out, and use some trigonometry to find these angles. However, in 3D, well, it kind of sucks. It's 3-dimensional space. It's not exactly easy to draw. It's not easy to analyze. So what do we do in 3D? Well, we actually use something called the dot product. All right, so dot product, dot product, dot product. I want you guys to associate angles with dot product. Okay, if you ever see an angle question, dot product. Hopefully I got that stuck in your head. Maybe a little bit annoying, and I apologize, but I really want you guys to remember that. Now you guys may be saying, Clayton, you're really hyping this shit up. What is the dot product? Well, it's actually a very nice simple formula where we take a vector A and we dot it with a vector B. Now, this gives us the magnitude of A multiplied by the magnitude of B times cosine theta. Now you guys may be saying, Clayton, what's so special? Well, if we look at the very right side of this formula, we have a theta there. And that theta is actually going to be the angle between vector A and vector B. So using this formula, we can actually find the angle between two vectors, which I said is going to be kind of the first question we have to answer in those exam questions. So if we have two vectors here, a and b, and I wanted to find the angle between them, which is that theta, I'm going to use the dot product. And you guys are saying, all right, Clayton, that's easy. If I look at the right-hand side, we have the magnitude of a. I know how to find magnitudes. Magnitude of b, piece of cake. Cosine of theta, well, I have a calculator, so I can figure out what that is. Oh, wait a second, what about that left-hand side? So this is where it starts to get a little bit tricky, is how do we calculate that a dot b? Well, it's actually really simple. Looks bad, very simple. That's actually most of engineering if you think about it. Looks really bad, it's actually pretty simple. So a dot b, if I define two vectors, a and b, a dot b is actually just going to be each component multiplied by each other added together. That's it. Now, you guys are saying, Clayton, whoa, you're talking a little bit too fast there. What exactly did you say? Well, all we're going to do is we're going to take the two x components, multiply them together. We're going to take the two y components, multiply them together, and the two z components, multiply them together. And then finally, we're going to add everything together. We're going to sum it up, basically. Now, here's kind of the thing here. If we're adding everything together, if we have all of our components as three separate piles, and we clump them all together and add them together, we are going to get a single number. All right, a single number because we're adding it all together. This means that a dot b actually produces a scalar. It does not produce a vector. It produces a scalar. And if you look at the title of this slide, I kind of hint to that because another name for the dot product is actually called the scalar product. Okay, so if you guys do a dot product and you somehow get a vector, you guys did something wrong, all right? It should produce a scalar, and the formula, as we can see, it's not too bad. Now, here's the first trick when it comes to dot product, and I find that a lot of the professors forget to mention this, and it creates a lot of confusion with students. We can dot any two vectors together. If A was a force vector and B was a position vector, no problem, we can do that. If A was a unit vector and B was a force vector, again, no problem, we can do that. You guys don't have to worry about making sure that the two vectors are the exact same. We're going to talk more about why that is in the next slide. Now, the last little trick here is that it's associated. Distributive. I always forget those words, and we're going to talk about them more in the next slide. But basically, a dot b, it's going to be the exact same as b dot a. So you don't have to worry about trying to get order right. And this is very simple. If we look at the formula, we're multiplying the two x components together. It doesn't matter if we go 2 times 3 or 3 times 2. At the end, it's going to be the exact same thing. All right. So when we look at the dot product, some of you guys may be saying, Clayton, I don't know, it seems pretty sketch. You seem pretty sketch. How about a proof? Well, no problem at all. Linear algebra and these dot product things, this is actually kind of my specialty. I teach solid mechanics, so I'm very used to this. Now, the dot product actually has a lot of different proofs, but I'm going to show you guys perhaps one that you guys find the most easy. And that is this. If I want to go a dot b, I'm going to essentially write out all of a, and I'm going to write out all of b, and we're going to start multiplying everything together. Now, the thing to keep in mind here when we're actually looking at this, and this is something we don't really talk about because you don't need to know, but I, j, and k, they're actually vectors. And they're more specifically, they are the vectors of the three-axis systems. So for example, I would be 1, 0, 0. J, which is the y-axis, would be 0, 1, 0. And k would be 0, 0, 1. Again, not something you really need to know, but for this proof, if you guys know that, it'll make a lot more sense. So let's say we multiply everything together, we end up getting something like this. Now this looks like complete ass, and you guys are saying, Clayton, you're supposed to prove it, not make it worse. I'm sorry, but don't worry, this simplifies very nicely. Because remember, for the dot product, we had the following formula, where a dot b, or two vectors dotted together, is equal to the magnitude of the two vectors multiplied by each other, and then multiplied by cosine theta. Now, remember what I said, I, j, and k are actually the three axes. So if we were to consider two vectors that are the exact same and dotted with each other, well, we know that's actually going to be equal to 1 because the angle between them is 0. If I were to take the y-axis going up and try and find the angle with the y-axis, well, they're the exact same. So of course the angle between them is going to be 0. Cosine of 0 is equal to 1. Therefore, anything where we got I dot I or J dot J or K dot K, we know it's going to be equal to 1. So we can take out those three components right off the bat. Now the next thing is if we dot two axes that are not the same, so let's say I take the x-axis and I dot it with the y-axis, well, we know the angles between them are always going to be 90 degrees. So in this particular case, if we have I.j, j.k, or I.k, we know it's always going to equal 0 because it's 90 degrees. Cosine of 90 is equal to 0, so therefore we can cancel out a buttload. As we can see, we're actually only left with three components. That is ax bx, ay by, and az bz. So therefore a dot b is actually equal to ax plus bx, or sorry, ax times bx plus ay times by plus az times bz. Again, nice and simple. Now, the dot product has three properties that, well, I'm going to say you should remember, but you don't really have to remember them. It's one of those things you should have them in the back of your mind, but I've never seen them actually tested. I'm going to be honest with you guys. And the first one is commutative, which means that a dot b is equal to b dot a. Again, that's the one I mentioned on the previous slide. I got the name wrong, of course, but this is going to be kind of the nice one to remember because a lot of students start freaking out about order. Remember, in position vectors, it's very important if you go from b to a or a to b. They give you a different answer. Dot product, you don't have to worry about that. So a dot b is equal to b dot a. Nice and good. The second one is associative. So if I were to take a scalar c and multiply it by a dot b, well, that's the same as multiplying a by c and then dotting with b, etc., etc. Again, this is one I've never really seen tested. You don't have to worry about that too much. And the final one is distributive. I don't know why. I can't say these three words. I always struggle mightily. So if this is the case, if we have b plus c and then dot it with a, well, that's the same as going a dot b plus a dot c. All right, so again, the only real one that I would recommend remembering is that the order doesn't matter. You can go a dot b or b dot a. You guys will be fine either way. So the next question becomes, all right, I'm now the expert of the dot product. What can I do with the dot product? Well, we're going to answer that first question we talked about, which is the angle between vectors. I almost guarantee you at some point in your midterm, especially at the University of Alberta, but if you guys are elsewhere in the world, I almost guarantee that one of the questions or part of the question will be the angle between two vectors. It's very important. It's a very important topic. At least professors really view so. So what we're going to do is we can use the dot product to find the angle between two vectors. Now, let's say I wanted the angle between a force vector and a position vector. Well, all I have to do is use my specific formula that I had before. As we can see, I have a nice cosine theta. I can figure it out. Now, this is where I'm going to really emphasize what I said before, in where it doesn't matter which two vectors you dot together, it'll always work. So let's say in this particular case, the red vector was our force vector, and the purple vector is actually our position vector. I can use the formula on the left to find this angle theta. Now this is important because the real secret to engineering exams isn't so much the knowledge. You guys are all incredibly smart. You guys think, Clayton, you're being modest. No, you trust me. You guys are smart and professors know this. So they don't really test you on things that are hard. They test you on how fast you can solve things, all right? How fast. So normally when students see this angle between vectors, they think, oh, I need to convert the position vector to a force vector and then dot the two force vectors together. Now you can do that. It's going to give you the right answer, but it's that extra step of converting the position vector to a force vector that's going to take up your time. Again, the key to these exams in engineering is solving things as efficiently as possible so you have enough time to finish the exam. University of Alberta here, we have around 1,200 kids taking the midterm, and I've only ever seen fully completed midterms maybe 30-40% of the time. Kids tend to run out of time. That's the major problem. So any sort of trick you guys know will always help you. Now you guys may be saying, all right, Clayton, well, I'm going to believe that it doesn't matter which vector, but how can you prove it to me? Well, it's simple. If we were to rearrange the formula, we get this, where the cosine of theta, which is the angle between the two vectors, is equal to f dot r divided by the magnitude of f divided by the magnitude of r. Now notice how we're dividing by the magnitude of both of the vectors. And we remember before, when we divide by the magnitude, we're essentially getting unit vectors. And that's what we're essentially doing, is we're taking these two vectors, we're scaling them down to unit vectors, and then calculating the angle between two unit vectors. And that's why it's valid, because we're not actually dotting a force vector and a position vector. We're basically just dotting two unitless vectors together to get the angles. Now, this is nice because we can expand this above, because we know what f dot r is. It's going to be the x component of f multiplied by the x component of r plus the y component of f multiplied by the y component of r, etc. And we have this nice formula. So in an exam type scenario where they ever say, give me the angle between these two vectors, if you know the components of both of the vectors, you can find the magnitude, so that's everything in the denominator, and you have everything for the numerator. Therefore, you guys can very quickly solve for everything, because we know the right-hand side, and now we know what the left-hand side is. Now, there's one more trick that'll save you guys some time, and that is this. If we look at this formula, it's dependent on the magnitude of the vectors we want to dot together, aka the two vectors we want to find the angle between. Now remember that the magnitude of a unit vector is actually equal to 1. That's going to be a very important thing here, because if we look at the denominator and we want to dot two unit vectors together, or find the angle between two unit vectors, well, the bottom is going to be 1 times 1, which is just 1. So if I have two unit vectors, well, the angle between them, cosine theta, is simply just going to be the dot product of them. I don't have to divide by the magnitude, which is great. So that's kind of another little thing to save us some time. So that's going to answer the first question, the angle between vectors. How about the second question, which is something called projections? Now, projections is a fancy word to describe it when we want to find the component of something in an arbitrary direction. So a direction that is not very common, if you will. Now, the best way to show you guys what exactly this is through a picture. So let's say that I have my force vector in 3D, and you guys are saying, all right, I even have the x component, y component, j component. Now, if I were to ask you guys in a test, what is the x component? You guys are just going to laugh at me. You guys are going to say, Clayton, the x component is clearly that component along the x-axis. It's going to be f of x. I'm going to say, all right, what about the y component? Well, that's going to be the component along the y-axis, and that's going to be the second component in our CVN. And the j component is going to be the same thing. It's going to be that f of z. It's going to be the component aligned with the z-axis there. So now the question becomes, what happens if I ask for the component along an axis that is not x, y, or z? So this is what a projection is when we want to try and find a force component that is in an arbitrary direction. Now the direction has to be defined. So typically what we do is we give you a unit vector to define the direction. And we say, I want the component of f that is in the direction of this unit vector. So what we actually want is we want a force vector that looks something like this. So it's the component of f that is parallel to that unit vector. So that's why I call it f parallel. Now, the trick to solve this is actually to create a right triangle. If I know the parallel component, well, then I can also find the perpendicular component, and this actually creates a right triangle where the parallel meets the perpendicular. That's actually 90 degrees. It doesn't look like it because we're in three-dimensional space, but it's actually 90 degrees. So now we've created a triangle. The hypotenuse is going to be the magnitude of our force vector, and the two components are going to be f parallel and f perpendicular. So you say, all right, well, right triangles are great if I have one of the angles. So let's say I knew the angle over there between the force vector and our unit vector, which is theta. Well, then I can start to solve for things. So let's take a look at what this would look like for the dot product. So if I were to dot my force vector with that unit vector, we know the formula is going to be the magnitude of the force vector multiplied by the magnitude of the unit vector multiplied by cosine of theta. Now, if we look kind of in the middle there on the right-hand side, we have the magnitude of the unit vector. Well, the magnitude of a unit vector is simply equal to 1. So we can just take it out of the formula. It doesn't really matter. So now this is where all that sexy magic starts happening, because we now know that f dot u is equal to the magnitude of f times cosine of theta. And if we look at our triangle over there on the right, the magnitude of f, that's the hypotenuse. So if we have the hypotenuse of a triangle, the angle, and its cosine of theta, we're actually solving for that adjacent component. In this case, that's that f parallel over there. So we can conclude that f dot u is actually equal to the parallel component. So if you guys ever have a question where they want the component in an arbitrary direction, all you guys need to do is take your force vector and then dot it with the unit vector defining that direction. That's it. It's actually nice and simple. It sounds really bad, and that's where students start getting mixed up, is they think arbitrary directions. I don't know how to do that. It's nice and simple. Just define the direction as a unit vector and dot it with the force vector. Now, the key thing here, and please keep this in mind, is that this is going to be the component of our force vector in that direction of u. And by component, I mean it's going to be a single number. Look above at the formula, we're taking a force vector and dotting it with a unit vector. Remember that the dot product always produces a scalar. So in this particular case, it'll give you the component in that direction. Now, if the question wants the vector f parallel, well, that's simple, because remember, a vector is simply going to be a magnitude multiplied by the direction. In this case, the magnitude, f parallel, well, we solved for it above, we know what that is. The direction, well, we know it's aligned with that unit vector, so we have that. Therefore, we can find f parallel as a vector fairly simply. Now, sometimes the professor might be real mean, and they say, okay, well, f parallel is all nice, but I'm very interested in f perpendicular. Everything we talked about right now has to do with f parallel. Well, what about that perpendicular component? Well, actually, this is really simple too, because keep in mind that the force vector f is actually made up of f parallel plus f perpendicular. So all I have to do is rearrange that very simple formula, and I can say that f perpendicular is simply going to be my force vector minus that parallel component. It's that easy. Now, this, since we're subtracting two vectors, it'll result in a vector. So this will be the perpendicular vector. If we wanted the perpendicular component, well, we have the vector, we have its three components. We can use our magnitude formula to actually find that component rather simply. But as you guys can see, this is clearly the worst when it comes to that first exam question, because it can be a lot of work to determine something that's actually really simple. But yeah, that's it for this video. I hope I was able to explain this well. I tried being more serious when it comes to this stuff, because again, in my experience with students, this is usually the first step in the course where the mistakes start happening. Now, don't worry, if you guys are still looking at this and saying, Clayton, I don't know what you're talking about, I will have two examples down below. I will have one for finding the angle between vectors, and then I will have one, of course, for projections. So if you guys are still lost, which I don't blame you, I'm not the best at looking at theory and completely understanding, please refer to the examples. I'm a big believer that examples are the way to go in this course to really help you learn what's going on. But yeah, that's it for this video, guys. Thank you guys so much for listening. I hope you guys have a wonderful day, and hang in there. The second week can be pretty rough, but week 3, which we're going to start in the next video, it gets a lot easier. So again, thank you guys so much for listening. I hope you guys have a wonderful day. I will see you guys in the next video.